तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We have seen what are rules of inferences in deduction and how we can use them to find out whether an argument is valid or not. We have also seen what is meant by a conjunctive normal form, a disjunctive normal form, and we have also seen how to bring a well formed formula of propositional logic to conjunctive normal form or disjunctive normal form. Now we shall see how to use the resolution principle to find out whether an argument is correct or not. So, we shall concentrate on the resolution principle. A variable or negation of a variable is a literal, it is called a literal, and you know that a disjunction of literals is called a sum and a conjunction of literals is called a product. A clause is also a disjunction of literals, it is a sum. A clause is a disjunction of literals. Now, what do you mean by resolution? From any two clauses C1 and C2, if there is a literal L1 in C1 that is complementary to a literal L2 in C2, then delete L1 and L2 from C1 and C2 respectively and construct the disjunction of the remaining clauses. The constructed clause is a resolvent of C1 and C2. This is the definition of a resolvent. What is meant by a resolvent? So, it is like this. Suppose you have two clauses. Maybe I shall fill this with some Q, not R, something like that, not S, R, P, R, T, R, this is a class, it is a distinction of literals and is called a class. This is also a class. This is a literal, this is a literal, this is a literal and this is a literal. Now, in this class you have a variable and in this class you have the negation of that variable. So, this literal and this literal are complementary to each other. Then the resolvent of these two classes is obtained by deleting these two and getting the disjunction of these two, that is Q R not R, R not S, R T, R U. Combine these two, that is called, this is the resolvent of this and this. Now, how can we make, for example, modus ponens, you know that P and P implies Q is Q. If I express this in logical form, the P, PRQ I can write as not PRQ. So, what is the resolvent of these two? You have to remove this and you end up with Q. And similarly, modus tollens, you have P implies Q and not Q, from which you conclude not P. Look at it in class form, P implies Q you can write as not P or Q, and then you have not Q. Take the resolvent of this, you will get not P. This is just to show how the resolvent is connected to the conclusion. Okay. So, we will see the next one. Given two classes C1 and C2, a resolvent C of C1 and C2 is a logical consequence of C1 and C2. These two examples we have seen that there are two classes given, the resolvent of them is the logical consequence of the two, that you can see. Here again you can see that the resolvent of these two is the logical consequence. In general, how do you prove this theorem? It is a theorem. So, I have a class C1 in which I have a literal L, and remaining classes I can put as C1 prime, and I have another class C2 which contains not of L, and then the remaining classes I can put as C2 dash. Now, the resolvent C of C1 and C2 is, you remove these two and find the disjunction of the remaining portions. This is the resolvent of this. Now, we have to show that this is the logical consequence of this. Okay. Now, you must remember that this is a sum, this is also a sum, full having only R's. And what do you mean by the conclusion or the consequence? If the premises are true, the conclusion must be true. That is what we want to show. Now, the premises are true, say. Then there are two possibilities, either L is true or not L is true. L is false, that is this is equivalent to saying L is false. Either L is false or L is true. Suppose L is false. In that case, look at the C1. If this has to be true, then C1 dash has to be true. That means C1 this will be true, C1 prime or C2 prime will be true. If L is true, then not L will be false. So, in the second class this is false. So, in order that the second class be true, this must be true, and if this is true, the whole thing is true, because everything is only disjunction. So, you see that when you remove this L and not L from two classes and construct a disjunction of C1 prime and C2 prime, either C1 prime will be true or C2 prime will be true, depending upon whether L is false or L is true, and L has to be either false or it has to be true, one of them should happen. So, ultimately the class C1 prime or C2 prime will be true. So, whenever these two classes are true, C will be true. That is why C is the resolvent of C1 and C2, and this is the major result using which we find out whether an argument is valid or not. So, what is the resolution principle? This is the resolution principle. Given a set S of classes, a resolution or deduction of C from S is a finite sequence C1, C2, Ck of classes such that each C is either a class in S or a resolvent of classes preceding C, and Ck is equal to C. A deduction of the empty class from S is called a refutation or a proof of S. So, look at this example which you have already considered. This is a class, I mean it contains only a single literal, this is also a class, and the resolvent of these two is Q, which is the logical consequence. Okay. So, here from some classes you are getting more and more classes, and finally you derive the conclusion. Now, if you want to look at it as a refutation or a proof, instead of considering like this, the final conclusion you take the negation of the conclusion and then you derive the empty class from that. So, here instead of taking these two, you also take the negation of the conclusion, and you can see that if you find the resolvent of this will be Q, and if you resolve these two classes you will get the empty class. This is called a proof or a refutation, and in this case it will be like this: the resolvent of these two is not P, and you have to take the negation of the conclusion, which is P, and so you get the empty class from that. This is called a refutation or a proof. I will once again repeat this, that is, you have a collection of some set of classes C1, C2, etc., and you want to derive a conclusion from that. What you have to do is try to resolve some of them and get more and more classes, make use of the resolution principle, and finally whatever you want to conclude, you can take the negation of that and then arrive at the empty class. This is, if this works out correctly, then the argument is correct. If it does not work out correctly, the argument is not correct. We have considered some examples to find out whether an argument is valid or not. Let us take the same example and work them out using resolution principle. This principle is called the resolution principle. So, let us take the second and the third example, in which we already considered. It is, let us take the third one first. If today is Tuesday, then I have a test in computer science or a test in economics. If my economics professor is sick, then I will not have a test in economics. Today is Tuesday and my economics professor is sick, therefore, I have a test in computer science. We know that this argument is correct. Let us see how to prove it using resolution principle. So, today is Tuesday. T, I have a test in computer science. I have a test in economics. E, my economics professor is sick. So, how do you write the arguments? If today is Tuesday, then I have a test in computer science or economics. If my economics professor is sick, then I will not have a test in economics. Today is Tuesday and my economics professor is sick, therefore, I have a test in computer science. And we have seen that using mod opponents, etc., we can prove this. Now, let us try to write them in class form. So, the first one you will write as not T or CS or E. P implies Q can be written as not P or Q, and you can even write, because R is associative, you can write it without the parenthesis. This is one class. Similarly, write this in class form, it will be not S or not E. And the last one is a conjunction, T and S. Actually, you have to take it as two classes. One class is just T, having only one literal, another class is just having one literal S. So, you have to split it like T and S. And the conclusion is CS. to derive the empty class you have to take the negation of the conclusion. So, you take not S and try to use the resolution principle. Now, I will write it as 1, 2, 3, 4, 5. From 1 and 3 this T will cancel with this, you will get CSRE and from 2 and 4 you will get, this will cancel with this and you will get not E, and from 6 and 7 you will cancel this and you will get CS, and from 5 and 8 CS and CS will get and you will derive the empty class. So, this argument is a correct argument because you are able to derive the empty class from that. This is called a proof or a refutation. You can see that instead of the usual procedure of deduction, if you use this, this is much more simple and this can be automated, and this is the one which is used in the logic programming language PROLOG. Now, let me take the second example and we shall see how to use the resolution principle for that. It is not the case that IBM or Xerox will take over the copier market. If RCA returns to the computer market, then IBM will take over the copier market. Hence, RCA will not return to the computer market. So, let us write it down. IBM takes over copier market. Xerox takes over the copier market. RCA returns to computer market. So, it can be written like this. It is not the case that IBM or Xerox will return to the take over the copier market. If RCA returns to the computer market, then IBM will take over the copier market. Therefore, RCA will not return to the computer market. This is the argument. Try to write it in, we have seen that this argument is correct. Try to write it in class form. The first one using De Morgan's laws can be written as not I and not X. This is not a class because it is a conjunction. So, as a class you have to write it as not I, not X, separate them and write it. This you can write as not R, Ri, not R, Ri, and you have to take the negation of the conclusion. So, that is R, and from this you must be able to derive the empty class. So, consider this as 1, 2, 3, 4. So, from 3 and 4 you get I, cancel this and you get I, call it as 5. Then from 1 and 5 you get the empty class, this will cancel with this. You have not made use of the second one, that is fine. It is not necessary you should make use of every class in the argument. Even without making use of something you are able to derive the empty class, that is fine. So, the argument is correct. So, this is how the resolution principle works. Okay. This is very much used in the logic programming language PROLOG. It is used in artificial intelligence applications. So, let us see what is the logic programming language PROLOG and how the resolution principle is used in that. The logic programming language PROLOG has some rules and facts, or I should rather say facts and rules. What are facts? facts are something written like this, like female Mary likes Mary books, likes Mary chocolates, like that. This will stand for the fact Mary is a female, and this will stand for the fact Mary likes books, and this will stand for the fact Mary likes chocolates, and so on. So, actually you give a lot of facts to the system, and then you also have some rules. Making use of that, if you ask some questions, it will reply. For example, in this case, if you ask a question, is female Mary, the question is Mary a female, then it will come out with the answer yes. Or if you ask something like is female John or something like that, it will say no. You can also ask questions like this, likes Mary books, which will mean does Mary like books, it will say yes. Or if you ask questions like likes Mary X, what does Mary like, then X, it will say X is equal to books. It depends on which one you have given as the first one. So, if you have given this before this fact, then it will say this. Then if you press a semicolon or something, sometimes depending upon the implementation of the language, next if you ask again, it will say X is equal to chocolates. And then afterwards if press, it will say no, nothing else is there. So, like that you can ask questions. You given some facts, we can ask questions and get the answer. Now there are some rules also, something like like brother XY if male X parent XMF parent YMF. This should be interpreted as, when do you say that X is the brother of Y? When X is a male and also X and Y have the same mother and the same father. Parents of X are M and Y. M is the mother, F is the father, and similarly Y also has the same mother and the same father. Then you say that X is the brother of Y. This is called a rule. Now you can, this is a general rule and you can instantiate it. When you instantiate, it will be like this: brother Ram Lakshman you must give the same value for X here. So, male Ram, this comma usually represents AND in the logic. Parent Ram. Now, here there is a Ram, mother is Sudha, say Sudha, Sridhar, some name. comma parent Lakshman like that. They have the same parents Ram and Lakshman, and Ram is a male. So, this when you instantiate you get something like this. Now, a Hahn class is like this. A Hahn class is again a distinction of literals, but all of them will be negated except one, or either all of them will be negated or at most one may be non-negative literal. So, it is a distinction of literals where at most one literal is non-negated. All of them can be negated also. If it has, if a Hahn class, if it has one non-negated literal, it is called headed Hahn class. If all literals are negated, it is said to be headless class, headless Hahn class. Now, in the prologue sense, this is looked at as a class, and this portion is the head, this is the head, and if you derive something from some facts and rules, if you have something like this, this is called headless class. Now, this can be in the if then form, it can be read like this. Look at this, it can be read like this. If X is a male and parent of X are M and F and parent of Y are M and F, then X is the brother of Y. So, this is the if portion and this is the then portion. You have to read it like that. A fact, a single fact like likes Mary books, something like that. This is just one literal and it is a headed Hahn class with just one literal. So, a fact is a headed Hahn class with just one literal. Let me take one example and show how this works. I will write both in the if then manner and also in the logical in the prologue manner and see how they correspond with each other. Okay. So, first we will write like this: aunt xy, x is the aunt of y, this represents x is the aunt of y. In that case, female x sister x z, x is the sister of z and parent z y. So, if X is a female and X is the sister of Z and Z is a parent of Y, then X is the aunt of Y. This, if you want to write in the if then else notation, I will write like this here. If X is a female and Z is the X is the sister of Z and Z is a parent of Y, then X is the aunt of Y. Now, when you say it as a rule, in general when you write it, it would mean for all of X, for all of Y, for all of Z. How would you write it as a logical notation? For all of X, for all of Y, for all of Z, female X and sister XZ and parent ZY implies aunt XY. Then suppose you have these facts. You have the facts female Mary, sister Mary John, parent John Joseph. Then from this you can conclude aunt Mary Joseph. Now, here in the prologue how it will do is, you have these facts, you have this rule, and first, and this is the your question is, suppose you are asking is is Mary the aunt of Joseph, then it will say yes, and in order to derive that it will take this and it has to satisfy this one, and this is called the goal. This is called the goal, and the prologue interpreter will try to find out whether this goal is satisfied. And for that, when it searches aunt, it finds a rule like this. So, it will try to instantiate aunt xy, that particular rule, it will try to instantiate. We have already seen what is meant by universal instantiation, universal generalization, existential instantiation, etc. So, when you try to instantiate and take X to be Mary and Y to be Joseph, it can be something like this: aunt Mary Joseph then female Mary comma sister Mary Z, parent Z Joseph, and it will try to find out whether there is a fact satisfying sister Mary and so on, and it will find this and it will also find this. So, you have Z taking Z to be John, this will be satisfied. So, when you instantiate you get this. Now, let us write it here. If you instantiate with x and y and z, you will find that you can write something like that: female Mary and sister Mary John and parent John Joseph implies aunt Mary Joseph. Now, write it in class form. When you write it in class form, you will have not of the whole thing or aunt etc. Not of this whole thing, and not of this whole thing, you have two ands here. Using De Morgan's laws, this will become a class like this: not female Mary or not sister Mary John or not parent John Joseph or aunt Mary Joseph. Okay. So, I will try to rub this off because we have already seen that. And we have these facts. So, this is a class, it is a headed class with this. Now, you have facts like female Mary then you also have fact like sister Mary John and parent John Joseph. Now, what you want to conclude is Aunt Mary Joseph. This is what you want to conclude. Okay. So, you have to take the negation of that, negation of the conclusion, that is not Aunt Mary Joseph, and from this you must derive the empty class using resolution. We can very easily see that. Take this class which has got 4 parts, 4 literals, this, and when you try to resolve using this, try to use this first. When you resolve, you will get the remaining 3 classes. Then when you try to resolve this one with the second one, this will get cancelled and you will have these 2. Then when you try to resolve this with the third one, this will get cancelled and you end up with this, but you have taken the negation of that. So, when you try to resolve this and this will get cancelled and you will end up with the empty class. Okay. So, you conclude that Mary is the aunt of Joseph, or you derive this conclusion, Aunt Mary Joseph. So, in this is a general rule, and when you instantiate you get this. This is looked at as a headed Hahn class. This is the head and this is the remaining portion, and each one of these is a fact that is also called a headed Hahn class. There is no negation part, it has only one literal and it is a headed Hahn class. And the goal or the conclusion is this, you want to derive this from this and this, and this is a headless Hahn class. So, when you try to do this resolution, from this you see that you will be able to get this. So, in order to have an argument or some sort of a goal satisfied, the goal is written in this and that will be the only headless class in that argument. You need to have only one headless class. Rest of them will be headed Hahn class like this. It could be an instantiation of a rule like this, where you have the head and the other portion. Each fact is a headed Hahn class where there is no negated literal, and the last conclusion which you derive from this is a headless Hahn class. Here also you look at like this. See, this the first one you wrote it as a class in the R form. You see that this is negated, this is negated, this is negated, but this is not negated. It is a headed Hahn class where this is the only non-negated one, the rest of them are negated. Each one of them is a Hahn class. This is headed, this is headed, this is headed, but this is not headed, and with this one headless Hahn class you will be able to use resolution and derive the empty class. This is the resolution principle used in PROLOG, and it is very automatic, and this is a very good principle. If you want to find out whether an argument is not valid or not using like mod exponents, distinctive syllogism, hypothetical syllogism, etc., it will be difficult. You have to use your own idea and do it, but this process is rather automated. Resolution principle is rather automated and you can program it. That is why this sort of an idea is used in PROLOG interpreters, and you can understand the principle behind it. One more thing is, actually in the PROLOG, this is the goal. You want to find out whether Mary is the aunt of Joseph. So, this is the goal to be satisfied, and you want to find out whether this goal will be satisfied. For that, you will try to find out whether there is a rule where you can instantiate, or whether there are corresponding facts which will satisfy this one, and so on. So, starting from the goal, it will try to find out whether it is possible to derive the entire thing starting from rules and facts, and this process is called backward chaining. Backward chaining. That is, you start from the conclusion and see whether the conclusion can be derived from the facts and rules. A forward chaining method, you start with axioms and then try to use the rules of inference and derive at the conclusion. That is the forward chaining method, but here the backward chaining method is used. Next topic which we will consider is methods of proof. In school and in earlier days you would have heard of theorems, proofs, etc., and you know what it is meant by a proof. But now we shall see the same idea from the logical point of view, how a theorem looks like as a logical statement and what sort of a logical idea you use in proving a theorem. There are several ways of doing it. All these things you already know, but still we are going to look at this methods of proof from the logical point of view. So, you know that starting from some axioms and rules of inference, you prove a result, and that is called a theorem. Now, how are theorems proved? There are several ways in which you can prove theorems. By its form, one is by its form. The form of a theorem or the statement may look like a tautology, and because it is a tautology, it is proved. A tautology is always true, so it will be proved. For example, something like this. 5 is even or odd. I can say this I can write in logical notation E5 or O5, or in essence you can write it as E5 or not of E5. This is P or not P, which is a tautology, so it will be always true. This is when you represent as a proposition. In general you can have something like for all of x where x is an integer, E of x or O of x. Every integer is even or odd, and this is a valid statement. This is a valid statement because it is equivalent to saying for all of x, E of x or not E of x, and this is a valid one, always true. So, because of the form or the way in which the statement is made, because it is a tautology or a valid statement of the predicate calculus, it holds, the result holds, the theorem holds, and this is one method of proof. So, when the statement of the theorem is in the form of a tautology or a valid well formed formula of predicate logic, it is a theorem. You need not have to prove something beyond that, just by its form it is true, and so it is a theorem. We have heard of several types of theorems, proofs, etc., and most of the theorems you may have statements like P and Q and so on. If the statement is of the form P and Q, you have to prove both P and Q. If it is of the P or Q, if you are able to prove one of them, it will be true, and so on. And in general, most of the theorems, the statement will be of the form P implies Q. If then, if you look at the statements, for example, if ABC is a triangle, if ABC is a triangle, right angled at B, then AC square is equal to AB square plus BC. This is Pythagoras theorem, and it is of the form if then. Okay. Now, if the statement of the theorem is of the form if then, what sort of methods you will use to prove this? Now, this is an implication. P implies Q, it is an implication. We know that the implication is true if P is false or Q is true, and it is false only when P is true and Q is false. Now, here sometimes you will be able to prove very easily that P is false. The statement of the theorem P implies Q, sometimes you may be able to prove P is false, or you may realize that P is false. In that case, the implication will hold. P implies Q will automatically hold. Such a proof is called a Vacuous proof. Vacuous proof. You need not have to prove anything else. If you just show P is false, the implication will hold. Usually, in some theorems, as a particular case, you may have to consider the case some n is equal to 0. It may hold for everything else, but for n is equal to 0, you may prove that this sort of a proof you have to use, and so on, like that. And in sometimes you may be able to very easily prove Q is true. Whatever may be P, you may be able to prove Q is true. In that case, the implication P implies Q will be true, and such a proof is called a trivial proof. trivial proof. And sometimes you assume P and then prove Q. This is called a direct proof. And sometimes you will prove the contrapositive, this is the third one. Fourth one, prove the contrapositive. Not Q implies not P, and this is called indirect proof. All these four things will be used in some case or the other. These two actually will be used at particular cases, some particular cases. We have what is meant by proof by cases, in that for specific cases we may use Vacher's and trivial proof. But generally mostly we use direct and indirect proofs. Let us take the direct proof. (10x plus 15y is equal to 102 if 10x plus 15y, then either x or y is not an integer. You can easily see that dividing by 5, this will be 2x plus 3y dividing by 5. Two x plus 5y is equal to 102 by 5. It is not an integer. Therefore, either x or y is not an integer. Either x or y is not an integer. This sort of a proof is called direct proof. Let us see later what is meant by an indirect proof. Let us give some example later. We shall also see some more methods of proof, like proof by contradiction, proof by cases, and so on. There is also something called existence proof, proof by induction, and so on. So, we shall consider some of them in the next lecture.